Hello, and welcome back for the final segment of Math Made Easy Pre-Algebra. Your hosts, Don Skinner and Vanessa Stewart, will take you on the final steps of your journey along the bridge from arithmetic to algebra. They'll begin with some number problems and show you how to write equations and solve them. Then you'll see how equations are used to solve real-life problems. The lesson will conclude with a second look at exponents. You'll have a chance to review what you've already learned and discover new properties of exponents. While you're working, you'll have another opportunity to check in with Casey and Tony, two hard-working employees of the East-West Tollway, and see how they deal with equations and exponents on the job. Before we begin, here are some tips to help you learn as much as you can from this tape. Keep paper and pencil ready and work along with Vanessa and Don as they solve each problem. You'll find a calculator very useful too. Press the pause button whenever you'd like more time to think about a concept or solve a problem. And remember the best part of working with a videotape. You can go at your own pace. Take a break whenever you need to, and be sure to rewind and review the tape as often as necessary until you understand all the concepts and examples. Now we're ready to begin. Here are Vanessa and Dawn.
Hello, and thanks for joining us for the final segment of Math Made Easy Pre-Algebra.
We'll begin with a topic that is closely related to the formulas you studied last time. Today, you'll learn to solve linear equations.
To introduce the subject, we'll start with some number problems.
Well, how about an example, Vanessa?
All right, Don, here's one. I'll pick a number and subtract 3.
You're going to tell me what number you picked?
No, but I'll tell you the result. It's 5. Now, you tell me what number I picked.
You picked a number, subtracted 3, and ended up with 5. Well, I'll just undo what you did by doing the opposite. I'll start with 5 and add 3. 5 plus 3 is 8. That must be the number you picked.
You're right. 8 was the number. 8 minus 3 equals 5. Now I'll pick a different number. I'll divide it by 6, and the result is negative 12.
You divided by 6, so I'll do the opposite. I'll multiply by 6. Negative 12 times 6 gives me the number you picked. That's negative 72.
Right again. I picked negative 72, divided by 6, and the result was negative 12. Now, do you have one for me?
Okay. I'm going to give you a two-step problem. First, I'll multiply my number by negative 2, then I'll add 7. The result is 15. Okay, Vanessa, what's my number?
Okay, I need to undo everything you did, so let me list your steps. Then I'll do just the opposite. You started with a number, multiplied by negative 2, added 7, and ended up with 15.
You got it.
So, I'll do the opposite operations in the opposite order to get back to the number you started with.
That sounds like a good strategy.
Okay, let's see if it works. I start with 15, then do the opposite of adding 7. That means I subtract 7. So far I have 8. Next I do the opposite of multiplying by negative 2. That's dividing by negative 2. 8 divided by negative 2 equals negative 4. That's got to be the number you picked.
You got it. I picked the number negative 4. Multiplied by negative 2 to get 8, then added 7 to get 15. Well, you've given us an interesting way to write out the steps, then work backwards to find the number. Now, let's give our viewers a chance to try your method.
Okay. Suppose I start with a number, then multiply by 5, subtract 3, divide by 6, and add 10.
Now you've used all 4 operations. What number do you get after all that work?
17.
You can see all of Vanessa's operations. Write the opposite of each of her operations, then follow the steps back up to find the number she started with.
When you find the number, check it. Do all the operations exactly as I did and make sure the result is 17. Press the pause button while you work and continue when you're ready.
Before we give you the answer, make sure that you did the opposite of each of Vanessa's operations. The opposite of adding 10 is subtracting 10. The opposite of dividing by 6 is multiplying by 6. The opposite of subtracting 3 is adding 3. And finally, the opposite of multiplying by 5 is dividing by 5. Use these opposites as you work your way back up from 17 to the original answer.
If you don't have the correct opposites, pause the tape and try again. Now, do you think you found my number?
Undo all of Vanessa's steps exactly as shown, and you'll find that the number she picked was 9.
That's right. Tell me how you found it.
Well, I undid everything you did by performing the opposite operations in the opposite order. You ended with 17, so that's where I started. Then I subtracted 10. That's 7 so far. Multiplied by 6, that's 42. Added 3, that's 45. And divided by 5 to get Vanessa's number, 9.
Nice work. Did you know you had the right answer even before I told you?
Yes, since I was able to check it. I started with 9, followed all your steps, and got 17, just as you did.
We've shown you one way to solve problems that involve an unknown number and the operations of addition, subtraction, multiplication, and division. Now we'll show you a more efficient way to write the problems and find the solution.
Let's go back to our first example and write it in the form of a sentence.
We can write a number with 3 subtracted from it equals 5.
Now, I'll write that as a mathematical sentence. I'll call the number x, and I'll write x minus 3 equals 5.
We have a mathematical sentence with an equal sign. It's called an equation. This equation has one variable, x. We'd like to find the value of x that makes an equation true. That value is called the solution of the equation.
We found the solution to several equations by undoing all the operations that were done to the variable. Let's show this work carefully using the properties of equality.
For the first problem, we'll use the addition property of equality. That is, the same value can be added to both sides of an equation. For this equation, we need to undo the subtraction of 3, so we'll add 3 to both sides of the equation. That gives the solution, x equals 8.
To check the solution, we'll replace x by 8 in the original equation and find out whether we have a true statement. As you can see, with x equal to 8, the left side and right sides are both equal to 5, so we've found the correct solution.
Here's another example. X plus 4 equals negative 3.
Now, to undo the addition of 4 and solve for x, we must subtract 4. The subtraction property of equality says that the same value can be subtracted from both sides of the equation.
On the right side of the equation, we have negative 3 minus 4. Remember that we can think of that as addition of the sign numbers negative 3 and negative 4. Then the solution is x equals negative 7.
And we'll check that. Substituting negative 7 for x in the original equation, we have negative 7 plus 4 on the left side. Then the left and right sides are both equal to negative 3, so the equation is true.
Here are 2 more equations that can be solved by the addition or subtraction properties. In the first, we solve for the variable n by subtracting 5 from both sides. On the left side, you see that 5 and negative 5 add to 0. The solution is n equals 13. In the second equation, we solve for the variable s by adding 6 to both sides. On the left side, negative 6 and positive 6 add to 0. But this time we won't write the 0. We'll go straight to the solution. S equals negative 1.
We've solved equations where a number is added to or subtracted from the variable. Now, let's try equations that involve multiplication and division.
We'll start with x divided by 5 equals negative 6. We undo the division by doing the opposite operation. That's multiplication. We multiply both sides of the equation by 5 and get the solution x equals negative 30. The multiplication property of equality justifies our work.
Next, we'll solve negative 7y equals 14. Y is multiplied by negative 7. To undo the multiplication, we divide both sides by negative 7. Then y equals negative 2. The division property of equality justifies our work.
Notice that we multiply or divide by exactly the same value that the variable is divided or multiplied by. The opposite of division by 5 is multiplication by the same number. 5, not negative 5. And the opposite of multiplication by negative 7 is division by the same number. That's negative 7, not 7.
Now, we're ready for some two-step equations. Here's an example. 3x minus 4 equals negative 10.
We need to use both the division and addition properties of equality to get the solution, but which one do we apply first?
To answer Vanessa's question, let's read the equation as we did at the beginning of the lesson. We take an unknown number, represented by x, multiply it by 3, then subtract 4, and the result is negative 10.
To work backwards and solve for x, we undo the subtraction first, then the multiplication. That is, first we add 4, then we divide by 3.
Showing the work in the equation form, we add 4 to both sides of the equation, which gives us 3x equals -6. Then we divide by 3 on both sides to get the solution. X equals -2.
To check the solution, substitute -2 for x. Be sure to write -2 in parentheses. Then the left side of the equation is 3 times -2 minus 4. That's -6 minus 4, or -6 plus -4. So the left and right sides both equal -10, and our solution is correct.
Here's a two-step equation for you to solve. X divided by 3 plus 5 equals 9.
Now remember to use the addition or subtraction property of equality first, then use the multiplication or division property.
Pause the tape while you solve the equation and check your solution. Continue when you're ready.
Did you find the correct solution? It's x equals 12.
To find the solution, you should have subtracted 5 from both sides of the equation, then multiplied both sides by 3.
When you check your solution, you find that both sides of the equation equal 9.
Now that you've learned the basics of solving equations, we'll take a second look at some special equations we introduced in our last lesson.
The special equations are called formulas. We worked with formulas for the area and perimeter of a rectangle in terms of its length and width.
We used other formulas for the circumference and area of a circle in terms of the radius. And here's one more. It's the formula for distance in terms of rate and time.
For example, suppose an airplane travels at the rate of 600 miles per hour. We can use the formula to find the distance the plane travels in 4 hours.
The rate is 600 miles per hour. The time is 4 hours. We substituted these values into the formula and multiplied to get the answer. The distance is 2,400 miles.
Notice that the formula helps us find the correct units for the distance as well as the correct value. Multiplying the units, we have miles per hour, or miles divided by hours, multiplied by the number of hours. The hours cancel and we are left with the correct units. The distance is 2,400 miles.
Now, let's try a problem where you know the distance and the time, and you need to find the rate. Vanessa, can you give me an example?
Sure, Don. Here's one about a marathon runner. He runs 26 miles in 2.5 hours. Let's find his rate. That is, his average speed for the race.
We can use the formula d equals r times t and substitute the two values we know. The distance, d, is 26 miles, and the time, t, is 2.5, or 2.5 hours. We need to find the rate, r.
The original formula is solved for d, but we need to use it to find r. That is, we need to solve the formula for r just as we solve the other equations we've discussed today.
We substitute the values for d and t and solve for r. R is multiplied by 2.5, so we'll divide both sides of the equation by 2.5. 26 divided by 2.5 equals 10.4, and that's the rate.
Well, the number looks right, but what about the units?
Well, since the distance is in miles and the time is in hours, I'd say that the rate has to be given in miles per hour. And let me check that by using the formula. 26 miles divided by 2.5 hours definitely equals 10.4 miles divided by hours, or 10.4 miles per hour.
That's exactly right. But you know, Don, something I said before wasn't exactly right.
Well, what was that, Vanessa?
I said that we worked with lots of formulas in our last lesson, but we can't take all the credit. Actually, Tony and Casey did most of the work.
You're right. They were very good at evaluating formulas. I wonder whether they're also good at solving formulas for a different variable.
Well, let's check in on them and find out.
I'm coming. Settler's office, Tony speaking. Yeah, hi, Donna. What's up? Well, tell me fast, because I've been in traffic for 10 hours and I cannot wait to get home. What do you mean bad news? I don't want to hear bad news. Are you sure you lost the numbers? No, I don't have a copy. Wait. Casey just came in. Maybe she has a copy. Hold on.
A copy of what? And why do you look so miserable?
The calculations and measurements we did yesterday.
Those lengths and widths and areas and stuff?
Yeah, Donna lost the memo. She can't find it, and the boss wants to check numbers tonight.
Great. I didn't keep a copy. I can't believe we have to do this all over again. Doesn't she have any of the numbers?
Bad news, Donna. Casey doesn't have a copy either. Well, are you sure you lost all the numbers? Oh, give me whatever you have. Right. Okay, 432 square feet for the area in the office. Okay, and the two fences, the perimeters, right? Okay, 401.5 feet. Well, that should be the high fence, the one that's in the parking lot. Okay, and 80.5. Well, that sounds familiar. No, the length was more than that. That must be the width. Okay, and the fence around the circle, that's 44 feet. Okay, what else? All right. Well, we'll go out, you make the measurements, and give you the list. Well, how long are you going to be there? Well, hopefully it won't have to take that long. All right. Okay, thanks. Bye.
I don't believe this. How could she lose all our measurements? Well, I am not going to start measuring again. It's her fault, so let her do it.
Look, don't blame Donna for this, Casey. She's having a rough time. You know, they're repairing her office, and it's a mess. They moved her desk, her papers, and she can't find anything.
Well, at least I get to measure the indoor stuff. You have to go outside in this awful weather to do yours.
If I help you with yours, will you help me with mine?
Sorry, Tony, there is no way you're getting me to go outside in this weather. But maybe we don't have to do so many measurements. Let's try those formulas that we used yesterday.
I don't think these formulas are going to work. Look at this one. See, Donna said that the area of the office is 432 square feet. Now, she found that out when she got the estimates for the new floor. But she doesn't have your numbers for the length or the width.
Wait a minute. I just remembered the length. It's 27 feet.
Are you sure?
I'm positive. See, 27 is my lucky number. Because I was born on the 27th. So I remember getting 27 for the length.
Do you have another lucky number for the width?
No, but I can solve for it. See, the area is equal to the length times the width. So that means that 432 square feet equals 27 feet times W. So since I have 27 multiplied by W, I have to divide both sides of the equation by 27 to solve for W. So that's 432 square feet divided by 27.
Well, I can do that. 432 divided by 27 equals 16.
Great. So 16 feet is the width.
That sounds about right. What about the perimeter? Don't you need to figure out how much molding you need?
Yeah, I do, but that's easy now that I know the length and the width. See, the perimeter is given in terms of L and W. So the perimeter is equal to 2 times the length plus 2 times the width. So all I have to do is substitute the values. So we've got 2 times 27 plus 2 times 16. And 2 times 27 is 54. 2 times 16 is 32. So that gives me a perimeter of 86 feet.
Do you think it'd be just as easy to figure out my numbers? See, Donna said the perimeter of the lot was 401.5 feet. Okay, she also mentioned something about 80.5 feet, and I'm pretty sure that that's the width. So if I substitute that into the formula, I just need to find the length, and I can work and find the area. You think I could use the formula the way you did?
Well, you can use the formulas, but not exactly the way that I did. So you have to start with the perimeter. Now, the perimeter is equal to 2 times the length plus 2 times the width.
Okay. Well, then I can just substitute, because I know the perimeter, right, 401.5, and I know the width. So I can go ahead and simplify. 2 times 80.5. So that would be 2L plus 161.
Right.
So how do I solve for the L?
Well, you have a two-step equation.
Oh, is that bad?
No, it just means that you have to solve it carefully. See, the first thing you need to do is undo the additions. So subtract 161 from both sides.
Okay, that's minus 161. Oh, well, I guess I have to copy this all over. I don't have enough room there to write.
No, actually, we don't need this anymore. Okay. So all you do is you write negative 161 plus 401.5. See, adding a negative number is the same as subtracting a positive number.
So can you help me figure this out?
Sure. Okay, so we have 161, I make that negative, plus 401.5, and that equals 240.5.
Okay. That equals 2L, right?
Mm-hmm.
How do you solve for L, though?
Well, that's the second step. Now you have to undo the multiplication.
Okay, so you have to divide by 2.
Mm-hmm.
Okay.
So 240.5 divided by 2,
Okay. So
that's
L
going to equal
equals
120.25.
20. That's got to be right, because I remember changing 3 inches to 0.25. Great, now I can figure out the area. All I have to do is multiply the length times the width.
Let me help you with that. Okay. The length is 120.25 times the width, which is 80.5. That equals 9,680.125.
Okay, 9,680.125 square feet.
Mm-hmm.
Great. Now all I have to do is finish the circle outside. You know, thank goodness Donna gave me the measurements for that fence around the circle also. It's 44 feet.
Right, so the perimeter of the circle is 44 feet. Now, I can't remember, do we use the same formula for that one?
No, Casey. That perimeter formula is for rectangles. The distance around a circle is the circumference.
Oh, yeah, and that's one of those pi formulas, right?
Right. The circumference is equal to 2 times pi times r. See, first I have to figure out r, and then I can do the area, and that's pi r squared.
Right.
So let's give this a shot. That's 44 equals 2 times 3.14, right?
Actually, you can use that for pi, but don't you remember that it worked out easier when we used the fraction to approximate pi? What was it? 22 sevenths.
Right, okay. So 22 sevenths for pi times the radius. Okay, so I should simplify that. Okay, that's 44 equals, I should simplify this, so that becomes 44 sevenths times r. Oh, wait a minute. R is multiplied by 44 and divided by 7. So how do I solve for r?
Well, you have to undo both operations. I don't think it matters which one you start with. So why don't we get rid of that 7 in the denominator first?
Okay, so I should undivide the 7. That means multiply both sides by 7.
Mm-hmm.
Okay, so 7 times 44 and 7 times 44.
So that takes care of the 7.
Okay,
Now let's get rid of that 44 that's multiplied by r.
so that means I should unmultiply or divide both sides by 44.
Mm-hmm.
Okay, 44 divided by 44. Well, this should be easy to simplify. That means r equals 7. Great, now I can just substitute r into the area formula. Thanks for showing me how to do this, Casey.
You're welcome. And thank you for showing me a good way to take care of fractional coefficients.
I did that?
You don't know it, but you did. Here, look at your work. See, you took care of the coefficient that was multiplied by r in 2 steps. First, you multiplied by 7, and then you divided by 44. But that's the same thing as multiplying the fraction 44 over 7 by its reciprocal.
Oh, and a reciprocal is an inverted number.
Right. To get the reciprocal, you switch the numerator and the denominator. So you showed me a good way to get rid of those fractional coefficients. You multiply both sides of the equation by the reciprocal of the coefficient.
Okay. Well, it's only going to take me a minute to figure out the area.
Okay, I'll start copying down these numbers.
Hey, you know
This
what?
time I'm keeping a copy for myself.
You know what?
What?
I mean, we really are good. I mean, with everyone else messing up around here, it's a wonder we get anything done.
I know. If they would just let us run the place.
Sounds like Tony and Casey are getting very good at problem solving on the job.
Well, that's right. They've been using the formulas they know to write an equation for each problem. Then they use the properties of equality to solve each equation.
For many problems, there is no formula that describes the situation. Then we use the given information to set up an equation.
That means we must translate the verbal statements given in a problem into mathematical statements. For example, suppose I tell you that a class has 7 more boys than girls, and I want to know how many girls and how many boys are in the class.
Well, you really haven't given me enough information to find out how many there are. But I do have enough information to give some examples. Suppose there are 12 girls. Then there are 7 more boys. That would be 12 plus 7, or 19. And if there were 20 girls in the class, then there would be 7 more boys. 20 plus 7 equals 27 boys.
Well, those are good examples. Now, suppose that X is the number of girls. How can you represent the number of boys?
I could introduce a new variable, but I don't need to. I can just say that the number of boys is 7 more than X. That's the same as 7 added to X, or X plus 7.
Right. Now I'll give you enough information to find both the number of girls and the number of boys. I'll tell you that the total number of students is 35.
The total is the number of girls plus the number of boys. Now, I'll translate the words into mathematical symbols to get an equation. I have X plus 7 equals 35.
You have an equation with just one variable, so you can simplify and solve.
All right. The left side becomes 2x plus 7, and the right side is 35. To solve the equation, I'll subtract 7 from both sides and simplify. That's 2x equals 28. Then I'll divide both sides by 2. The result is x equals 14.
That's right. Now, be sure to answer my questions and check your work using the words of the problem.
All right. The number of girls is x, so there are 14 girls. The number of boys is x plus 7. That's 14 plus 7, or 21 boys. The total number of students is supposed to be 35. 14 girls plus 21 boys definitely equals 35 students.
That's exactly right. Reviewing the problem, you see that we needed to write an equation with just one variable that we could solve. That's why it was so important to express both quantities, the number of boys and the number of girls, in terms of the same variable.
Now, consider a different approach to the problem. Suppose we use a single variable, but we assign it to the number of boys. For example, suppose we said that the number of boys is y.
Then the number of girls is 7 less than y. We start with y and subtract 7. That's y minus 7.
Vanessa is right. To indicate 7 less than a number, you mean the number minus 7. That's y minus 7, not 7 minus y.
Now we can solve the problem using an equation that looks different than the one we used before. Y minus 7 plus y equals 35. Simplifying, that's 2y minus 7 equals 35.
To solve, we begin by adding 7 to both sides. That gives 2y equals 42. Then we divide both sides by 2 and find that y equals 21.
Y represents the number of boys, so there are 21 boys. Y minus 7 represents the number of girls, so that's 21 minus 7, or 14.
The solution is the same as it was before, and it checks as it did before.
You've seen how to use the words more than or less than when you set up an equation. Other problems contain words such as twice as much or 3 times as much. Let's try a problem that involves all these phrases.
Okay, here's one. John works for his family's company. His sister works there too and earns $50 per week more than John earns. His brother also works for the company, but he earns $60 per week less than John.
Well, hold on a minute, Don. Let me start writing this down. I'll call John's weekly salary X. Then his sister's salary is $50 more than X. That's X plus 50. And for his brother's salary, I have to take away $60 from X. I'll be careful with that one. It's X minus 60, not 60 minus X. Now that I've got that straightened out, are there any other family members at the company?
Yes, 3 of them. John's cousin earns twice as much as he does.
Well, twice as much means 2 times as much, so that's 2 times X for John's cousin.
Oh, and next is John's uncle. Each week he earns $10 less than 3 times John's salary.
Whoa, that's a complicated one. Let me start with 3 times John's salary. That's 3X. Then I want $10 less than 3X. That's 3X minus 10.
You got it. Now, the last one. John's mom. Now, she's the president of the company, and she earns 4 times as much as John does.
Oh, well, that's an easy one. 4 times X, or 4X, for John's mom. All that information, and I still don't have enough to find out how much they earn.
Well, you need just one more piece of information. The total weekly pay for all 6 of them is $4,780. Now, you can set up an equation and tell me just how much each of them makes.
I'll write an expression for the total weekly pay. That includes John, plus his sister, brother, cousin, uncle, and mother. Now, altogether, the total is $4,780. So there's my equation. Now I have to simplify it and solve for X.
Well, let's get our viewers to help with that job.
Good idea. Help me solve the equation for X. That's John's weekly pay. Then find the amounts for all his relatives.
When you're finished, make sure that the total comes out to $4,780. Press the pause button while you work. Continue when you're ready to check your answers.
I found out that John earns $400 per week. Did you get the same result? If not, check carefully to see whether you simplified the equation as I did. First, I removed the parentheses. They were used only to group the salaries. No multiplication was indicated, so I just rewrote the equation without parentheses. Next, I combined like terms. Combining the X terms, I had 12X. Combining the constant terms, I had negative 20.
You can solve 12x minus 20 equals 4,780 in 2 steps. First, add 20 to both sides. That's 12x equals 4,800. Then divide both sides by 12 to get the result. X equals 400.
So, John earns $400. His sister earns 400 plus 50, or $450. His brother earns 400 minus 60, or $340.
John's cousin earns $800. His uncle earns $1,190. And his mother, the president, well, she earns $1,600. Check out the total, and you'll find that it's $4,780.
The equations we've been working on are called linear equations in one variable. In a linear equation, the variable appears to the first power only. Linear equations do not involve higher powers, like the square, cube, or fourth power of the variable. They also don't involve division by a variable, or roots like square roots or cube roots.
Now, we'll conclude our study of linear equations with one more problem. As we solve the equation, we'll write down the steps and finish with a general approach to solving linear equations.
Here's the equation. 2 times the quantity, 3x plus 4 minus 5, is equal to 4x minus the quantity, 6x plus 13.
We'll begin by simplifying both sides. On the left side, we multiply to remove the parentheses. Then we combine the constant terms. The left side simplifies to 6x plus 3.
On the right side, we apply the negative sign to remove the parentheses, then combine the x terms. The right side simplifies to negative 2x minus 13.
Notice that there are x's on both sides of the equation. We'll use the addition and subtraction properties of equality to collect the variable terms on one side of the equation and the constant terms on the other side.
That is, we'll add 2x to both sides of the equation. That removes the x term on the right and gives us 8x on the left.
Now, the equation looks like many others we've worked on. We'll subtract 3 from both sides to get the constant terms on the right side. Simplifying, we have 8x equals negative 16.
Finally, we use the division property of equality to solve for x. dividing both sides by 8, we have the solution, x equals -2.
To check the solution, we'll substitute -2 for x in the original equation. We simplify and find that both sides represent the number -9, so our equation is true when x equals -2.
We'll summarize the method for solving a linear equation. First, simplify both sides of the equation. Next, add or subtract equal quantities on both sides to collect the variable terms on one side of the equation and the constant terms on the other side. Finally, multiply or divide both sides by the same number to solve for the variable.
Well, now we've shown you how to solve linear equations. That is, equations where the variable has exponent 1.
As you move on in your study of math, you'll solve equations and problems that involve other exponents. It's important for you to remember what you've already learned and discover some new facts about exponents.
So, we'll conclude today's lessons, as well as our series on pre-algebra, with a second look at exponents and their properties.
Let's start with addition and subtraction of terms with different exponents. Remember that we can only combine like terms, that is, terms with exactly the same variable raised to the same power.
In Vanessa's example, 3x and 2x are like terms. We can combine them to get 5x. Remember, you add like terms and get a new term of the same type. X's and x's combine for a total number of x's, not x squares. The other like terms are -4y and +3y. We can combine them to get -y.
There are no other like terms in the problem. We have simplified to 4 different terms which cannot be combined.
Now, look at these expressions. Each has 2 terms. Can any of them be simplified to a single term?
Press the pause button for just a moment while you consider your answer.
Did you notice that there are no like terms in the expressions? So the answer to my question is no. None of the expressions can be simplified to a single term.
Now we'll consider a different operation, multiplication of factors with different exponents.
We'll start with a series of problems that look quite similar to our last set. This time, we're multiplying the same quantities we tried to add and subtract before. We can't simplify expressions that involve addition or subtraction of unlike terms. But now, we'll try to multiply factors with different exponents to see what happens.
Remember that exponents indicate multiplication, and parentheses also indicate multiplication. So the only operation involved in these expressions is multiplication.
The commutative property of multiplication allows us to change the order of the factors, and the associative property allows us to group them as we choose. So, we'll multiply the constants first. Then, we'll take care of the variables.
For the first expression, we have one factor of x multiplied by 2 more factors of x. X appears as a factor 3 times, so we can simplify the expression to x cubed.
In the next expression, reorder the factors, writing the constants first, then the x's, then the y's. The product of the constants is -20. There are 2 factors of x, followed by 3 factors of x for a total of 5 factors of x, and 2 factors of y followed by 1 more factor of y for a total of 3 factors of y. We simplify the product and write -20x to the 5th power y cubed.
In the last product, the constants multiply to -18, and there are 6 x factors and 4 y factors. We simplify to -18, x to the 6th power, y to the 4th power.
Now, look carefully at some of the products we just found. Can you find a pattern in the exponents? What happens when you multiply factors with the same base, raised to the same or different exponents? In general, how can you express the product of x raised to the power a and x raised to the power b?
Before you try to answer Don's question, watch for a few minutes as Casey and Tony explore a similar subject.
Oh, I'm in so much pain. I can't take much more of the boss's employee improvement plans. You know, yesterday's exercises almost killed me.
Well, that's because you didn't warm up properly. See, I'm doing my stretching now so that I'm ready for whatever he has planned. You know, whatever it is, I hope it doesn't take very long because we both got lots of shuttling assignments today.
Yeah, looks like a lot of miles, which means a lot of dollars. What's the deal with these charts?
You know, I don't know. This one in the middle looks like a multiplication table, but I'm not sure about these other tables.
A multiplication table? I haven't seen one of these in years. Let's say you multiply a number from here by a number from there. So 9 times 8. So you go across the column, then you come down. That's 72.
Right. You can also use it to divide. For instance, 56 divided by 7 equals 8.
Huh. You know, I never thought you could do that.
Good morning, shuttlers.
Morning, boss.
Morning, boss.
Are you ready for your morning exercises?
Yep, I've already done all my stretching, so I'm ready to go.
Well, that's good, Casey. But today you'll be exercising your mind. I hope you've been stretching that, too. Today's exercise involves those tables of numbers I left for you. I'm sure you recognize the one in the middle.
Oh, yeah, boss. It's a multiplication table. Hey, but you know what? You can also use it to divide.
You're quite right. But how about the other two tables? You're both awfully quiet. No ideas? How about that table on the right, Casey? I was sure you'd recognize it.
You know, it looks familiar, but I can't remember where I've seen it before.
Well, try to remember, because here's today's exercise. You know how to use the table in the middle to multiply and divide. The other two tables are different, but they can also help you multiply and divide. Tell me how and why it works, and I'll reward you with an extra 10 cents per mile for each mile you drive today. Good luck.
Extra 10 cents a mile, and I don't have to do anything to earn it. Where are you going, Casey? Oh, don't tell me you figured out the formula already.
Nope, and I'm not going to. I'd rather be out driving. I mean, what good is an extra 10 cents a mile if I get 0 miles because I spent the whole day here exercising my brain?
Come on, Casey. It's not going to take all day to figure out. Come on, we can solve this together. I'm sure this table here will give us a hint.
But how? I mean, on this table, you choose two numbers, you know that the product is on the table, and you know how to find it. Now, what has that got to do with these other tables, tell me?
So you multiply a number from here by a number from here, and you get a product on this chart. But hey, I think that holds true here, too. Let's see. For example, if we multiply 9 by 243, you get 2,187. That's right here. Why don't you try it on that table?
Oh, all right. How about 16 times 64?
16 times 64, that's 1,024.
And that's on the chart. Huh. But you know, what if you pick really large numbers? Like if I took these last two numbers, their product wouldn't be on the table.
You're right. It's over 500,000.
One thing I forgot to mention, shuttlers. Feel free to add as many lines as you want to the top and bottom of your tables.
He's a big help. As if I'd know what to write on these lines.
You know, I would guess that you just continue the numbers on this line, which, you know, would be 11, 12, and so on. But it's this column that's a mystery to me.
You know what? I think I just remember where I've seen this table before. We used one just like it the last time the boss had one of these brain teasers for us. Okay, let's see. It looks like a doubling table because each of these numbers in this column is double the number before it. So this next line would be 2,048, and I can keep doubling and add as many lines as I want.
But the boss said that we could add lines to the top and the bottom. I remember that there should be some numbers on the top. Do you remember what they are?
Let me think. Okay, we're subtracting 1 as we go up this column, so this should be 0, -1, -2, and so on. And here we're dividing by 2 each time, so this would be 1, and then 1/2, and 1/4, and I can keep going.
That works for this table. But what about my table? I mean, I could put the next number here. Okay. That would be 11. Okay. But what would I do with the column here? Wait a minute. This is a tripling table. So the next number here would be 3 times 59,049 equals 177,147.
Okay, now don't forget the numbers up top.
Oh, don't worry, I won't. I'll just extend them. And this number right here should be 0, and then -1, -2, and -3.
And then over here, you're dividing by 3 each time. So this should be 1, and this should be 1/3, 1/9, and 1/27.
Right. So now that we know that we can extend both columns in both directions, I bet you that we can multiply any two numbers on this column and find the answer in the same column. Let's call the boss.
Well, Tony, put the phone down. Wait a minute. What good is it if we know that the product is on the table somewhere? We've got to know how to find it. Like on this table, you follow the row and you follow the column to find the answer, but how do you find the answer on these other tables?
Okay, let's use an example that we did before. Okay. 9 times 243 equals 2,187. So you go across from the 9, there's a 2. You go across from the 243, there's a 5.
And 2 times 5 equals 10, so I bet the answer... Oh, no. I thought I had it, but I don't. I thought the answer would be here across from the 10, but that's not the right answer.
Wait a minute. I think I got it. 9 times 243 is 2,187. 2 plus 5 equals 7.
So what?
So that's it. You multiply two numbers from this list, and you add two numbers from this list.
I'm not so sure. Let's try one from my table. Okay, to multiply 16 times 64, I would add these numbers. 4 plus 6 equals 10. And that is where I find the product. 16 times 64 is 1,024.
Right. So we figured out how to multiply, but now what about how to use it to divide?
Okay. Well, that's got to be the opposite, right? So to divide numbers from this column, you would subtract numbers from this column. Let's try it. Okay. Let's do 19,683 divided by 243.
Do you know the answer?
Well, I would subtract the numbers in this column, so 9 minus 5 equals 4, and I bet the answer is across from here. I bet it's 81.
You got it.
Well, let's call the boss.
Whoa, Casey, put the phone down. Look, we're not there yet, okay? We know how it works, but we still don't know why it works. I don't know why, do you?
How about it's a miracle?
Casey, the boss is not going to go for that kind of reasoning. Look, just think. You said that he had given us that table before. I mean, don't you remember anything else about it?
Let me think. Well, I do remember that we said that it was an exponential table with a base of 2 because all of the numbers in this column are 2 times the number before it.
Okay, right. Okay, so all the numbers in this column are the exponents. So, for example, if you go down the column, 2 cubed equals 8.
Of course, how could I have forgotten? We found that all the numbers in this column can be written as powers of 2. Even this one, which is 2 to the 0 power, and these fractions, which are 2 to the negative powers. So how about your tripling table? Does it work the same way?
I don't know. I'm not sure. I think so. See, all the numbers in this column are 3 times the number before it. So my base is 3. Okay, so for example, 3 to the first power equals 3, all right? And 3 to the second power equals 9. 3 to the third power is 27.
But there's one line on both of our tables that's the same. When you have a 0 exponent, you get 1.
Oh, that's true. 3 to the 0 power equals 1. See, I also have negative exponents above the 0, which give me fractional values in this column.
Right. Now let's figure out why we can multiply the numbers in the right column by adding the numbers in the left column. Now let's see, we tried 9 times 243, and we found out that the product was 2,187.
Okay, I get it. So that means this would be 3 to the second power times 3 to the fifth power equals 3 to the seventh power. That means we have 2 factors of 3 times 5 factors of 3. Okay, that's 2, 3, 4, and 5 factors of 3. Huh. Oh, I get it. Okay, so that means it's 2 plus 5 factors of 3 equals 7 factors of 3.
And it should work for my base 2 table. So we tried 16 times 64, and the product was 1,024. So that's 2 to the 4th times 2 to the 6th. Now I don't have time to write all those factors like you did, but I know what I'd have if I did. I'd have 4 factors of 2 and 6 factors of 2, so that is 2 to the 4 plus 6, or 2 to the 10th.
Okay, so that now we figured the multiplication rule. When you multiply, add the exponents.
Now that's a general idea, but we got to be a little careful about how we say it. Now don't forget that you have to have numbers with the same base. Like, I don't think that it would work if we took a number off of your table and multiplied it by a number off of my table.
Okay, so for example, if we took 9 from my table and multiplied it times 4 from your table, it would be 36, and that's not on either table. Okay, we can adjust the rule. When you multiply numbers with the same base, you add the exponents.
That sounds good to me. Do you want to take a crack at the division rule?
How about to divide numbers with the same base, subtract the exponents?
Wow, that was quick. Are you sure it's right?
I'm pretty sure. Seems logical. Let's try one.
I'm working on it already. I'm trying 64 divided by 16, which equals 4. So using exponents, I would have 2 to the 6th power divided by 2 to the 4th power.
And I'm predicting that your answer would be 2 to the 6th minus 4th power, which would be 2 to the 2nd power, or 2 squared, equals 4.
Okay. Now let me see why that works. See, 2 to the 6th means that I have 6 factors of 2 in the numerator. So that's 4, 5, 6. And 2 to the 4th means that I have 4 factors of 2 in the denominator. So now I can simplify. I divide out 4 factors of 2 from the numerator and the denominator. And I'm left with 2 factors of 2 in the numerator.
Okay, so you have 1 in the denominator right now, and you started out with 6 factors of 2, but you divided out 4 factors of 2, so you're left with 2 factors of 2, which is 2 to the 2nd over 1, which is 2 squared, which equals 4.
Your rule worked great on that one. Let's try one from your table.
Okay, let's use one that we did before. 19,683.
So that's 3 to the 9th divided by 3 to the 5th. Now I divide out 5 factors of 3 from the numerator and the denominator, and that leaves me a 1 in the denominator just like before. And I'm left with 9 minus 5 factors of 3 in the numerator. So that is 3 to the 9 minus 5, or 3 to the 4th.
Right. So 19,683 divided by 243 equals 81. That's right, or 3 to the 4th. Let's go call the boss and rack up some miles.
Now wait, I'm still not sure that we've got it right. We've been dividing larger powers by smaller powers, but what happens if we do it the other way around?
Well, let's turn one of the equations that we were working on upside down. Okay, so 64 divided by 16 equals 4. Let's turn it upside down so we have 16 divided by 64, so that would equal 1/4.
Right, and when we do it using exponents, we have 2 to the 4th divided by 2 to the 6th. So now I divide out 4 factors of 2 from the numerator and the denominator, and I'm left with 1 in the numerator and 2 factors of 2 in the denominator. So that leaves me with 1/4.
That's right.
It's the same as your answer, but how does it work with your subtraction rule?
Okay. When I do it, I get 2 to the 4 minus 6 equals 2 to the negative 2.
But that's not the same as my answer.
Well, it doesn't look the same, but it is the same. You see, 2 to the negative 2 is the same as 1/4, or 1 over 2 squared.
You're right. 2 to the negative 2 is equal to 1 over 2 squared. You know, it just seemed logical when we said it before, because all of the numbers on the left column decrease by 1 as you go up, and all of the numbers on the right column are divided by 2 as you go up. But now we have another reason that 2 to the negative 2 equals 1/4, or 1 over 2 squared.
See, the subtraction rule works as long as we understand negative exponents. 2 to a negative power is the same as 1 over 2 to that same positive power.
And I have some other examples here. 2 to the negative 3 is equal to 1 over 2 to the 3rd, and 2 to the negative 1 is equal to 1 over 2 to the 1st.
Right. I think the same thing holds true for the base 3 numbers also. 3 to a negative power is the same as 1 over 3 to that same power.
You know, I think we've got it, almost. When we divide larger powers by smaller powers, we subtract the exponents and the quotient has a positive exponent. But when we divide smaller powers by larger powers, the quotient has a negative exponent. But what happens when you divide equal powers?
That's easy, Casey. Any number divided by itself equals 1. Well, take 64, for example. 64 divided by 64 equals 1.
Well, I know that, but how does it work with exponents?
Well, I'll show you. 2 to the 6th divided by 2 to the 6th equals 2 to the 6th minus 6, which is 2 to the 0.
And that's right, because we already discovered that 2 to the 0 power is equal to 1.
You know, I think the same holds true for 3 to the 0 power, because it equals 1 also.
I'm sure we found out everything that the boss could want. When we multiply numbers with the same base, we add the exponents. And when we divide numbers with the same base, we subtract the exponents.
Oh, and don't forget, any number to the 0 power equals 1. And also, any number to the negative power equals 1 over that base number to the same positive power. Oh, congratulations, Casey. Let's call the boss.
Yeah, but we better put that on speakerphone so we can both tell him, I don't want you taking all the credit.
Tony and Casey certainly earned their extra pay. And they also answered my question about multiplying numbers with the same base.
Oh, that's right, Don. They worked with base 2 and base 3, but their results should be true for almost any base number. To multiply numbers with the same base, add the exponents. And to divide numbers with the same base, subtract the exponents.
When you use the exponent rule for division, you may get a 0 or negative exponent. Remember what they mean. X to the 0 power is equal to 1, and x to the negative n power is equal to 1 over x to the nth power. Vanessa, you said these results are true for almost any base. Well, are there any exceptions to the rule?
Well, just one exception, Don. Division by 0 is meaningless, so in our division rule, or for 0 or negative exponents, the base cannot be 0.
There's one more important rule we should discuss. That's the rule of a power raised to a power.
Do you mean something like this? 7 cubed raised to the 4th power, or 3 to the 5th power squared.
That's exactly what I mean. And you might even have 7 to the negative 3rd power raised to the 4th power.
Let's give our viewers a chance to do these examples and find a rule.
Good idea. Now, for each example, express the answer using the original base. In problem 1, you have 7 cubed raised to the 4th power. That's 4 factors of 7 cubed, which means 4 groups of 3 factors of 7. Now, write the answer as a power of 7.
As you solve the problems, try to think of a general rule that will work for any base except 0. That is, x raised to the a power raised to the b power is equal to what power of x? Press the pause button while you complete the exercises, then join us for the conclusion of today's lesson.
Did you discover the rule? To raise a power to a power, multiply the exponents. In general, x raised to the a power raised to the b power is equal to x raised to the a times b power for any base except 0.
In the first example, there are 4 groups with 3 factors each. That's a total of 4 times 3, or 12 factors of 7. The result is 7 to the 12th power.
In example 2, there are 2 groups of 5 factors. That's 2 times 5, or 10 factors of 3. The result is 3 to the 10th power.
These examples suggest our rule. To find the number of factors, we multiply the exponents.
Problem 3 is similar to problem 1, but it involves a negative exponent. If our rule is correct, the power in the answer should be negative 3 times 4, or negative 12. Well, let's check it out.
Remember that 7 to the negative 3 power means 1 over 7 to the 3rd power. There are 4 groups of 3 factors, or 12 factors of 7 in the denominator. That's 1 over 7 to the 12th power, or 7 to the negative 12th power.
The rule worked with a negative exponent. Let's see if it works with a 0 exponent. We can try 8 to the 0 power cubed. And don't forget that 8 to the 0 power equals 1. So, the answer is 1 cubed, or 1.
The power rule gives us the same answer. The exponent in the answer is 0 times 3, which equals 0. Then 8 to the 0 power equals 1.
So, in summary, we have 3 rules for exponents. To multiply numbers with the same base, add the exponents. To divide numbers with the same non-zero base, subtract the exponents. And to raise a power to a power, multiply the exponents.
You've also learned the meaning of 0 and negative exponents. For any non-zero base, x to the 0 power equals 1, and x to the negative n equals 1 over x to the nth power. And that concludes our discussion of exponents, as well as today's lesson.
Make sure to practice all the skills you've learned today, as well as those you've learned earlier in the Math Made Easy Pre-Algebra series.
Rewind and review all the tapes as often as necessary until you understand the concepts and can solve all the problems.
Then you'll know that you've successfully completed your journey through pre-algebra. Once again, I'm Don Skinner, wishing you continued success in your studies.
And I'm Vanessa Stewart. Thanks for joining us. It's been our pleasure to work with you.